likewise, the mountain is perceived as being higher than it actually is. It has a little bit of terrestrial refraction as well. And so you can see how the red line comes in at a steeper angle than the orange line to the top of the mountain. So yes, we perceive the mountain as being a little bit higher than it actually is as well. But it's when those two angles align, the apparent angle of the mountain and the apparent angle of the star, that's when the occlusion happens.
So when the apparent angle of the mountain aligns with the apparent angle of the star in this explanation, is that a different angle than the geometric angle of the mountain aligned with the apparent angle of the star? Because it looks to me like both the red line and the gold line reach the same point and they intersect.
The red line approaches the observer from a steeper angle than the orange line. They both intersect at the observer, but the green line is forming a tangent with that red line where it intersects the observer.
Okay, but the red line and the gold line both converge at the peak of the mountain, yes? That's the physical mountain blocking that light ray.
Yes, but they have a different slope.
Okay, but we were talking about whether the star gets blocked by the physical mountain or not.
The star,
you said it doesn't. It gets blocked by the apparent mountain.
You say, okay, you're conflating physical mountain with geometric position of the mountain. Those are two different things, and I think that's what you're getting hung up on in your head, is you think that it's going to get blocked based on a geometric angle, because geometric to you sounds like, oh, that's the physical position. So it should get blocked when it hits the physical position. But what's happening here is that we see the mountain not at a geometric angle, we see it at a refracted apparent angle. And that apparent angle is the angle this red line is coming into the observer at. That angle that it's coming into the observer at is the same angle that's going out to this green line here, which is above the gold line or the orange line to the top of the mountain. So we see the star vanish at the point that the apparent angle of the star matches the apparent angle of the mountain.
So if that green line is where we see the mountain, and that green line is where we see the star, how would you ever know in your, portrayal of this, how would you ever know what the actual angles to these objects are if every apparent angle is a converged angle that you can't tell what the original incoming angle was until it reached you and became something different?
That's a great question, and I'm glad you asked that. I wish Alan had asked that question, honestly. So how do we know what the geometric angle is, right? Because we perceive the apparent angle. Well, that's the reason I did the weather balloon thing. That's why I used weather balloon data to work out what the refraction should have been based on the atmosphere. That would be like if I took the water tank, okay? Imagine I had sampled the salt concentration at every layer, like every millimeter of the water tank, going up the water tank, right? I could reconstruct what the ray was going to do with ray tracing by figuring out how it's going to interact with the water, what the density of the water is at each elevation, at each line going up the water tank, right? And I could reconstruct what that ray was going to do. From that, I could work out what the geometric angle had been if I knew how far away, say, the mountain is, right? I'd be able to work out what the geometric angle is to that mountain by basically reverse engineering and subtracting out the amount of refraction that I would expect given the concentration gradient of the atmosphere. With that said, this is exactly why I picked targets that were higher in altitude than the mountains that were generally observed, further away than the mountains were generally observed, to get a bigger delta between flat Earth and globe Earth, but also to minimize the effect of refraction. So if you look at my data, skip forward here. So here, we have the data off the airplanes, we have the data off the balloons, and all the way through with my data set, the globe is matching better. Now, the very earliest data point here, this shortest observation with a range of about 18 kilometers. Okay, not very high range. This was a balloon as well, and this was a balloon that was about, I want to say, 14 kilometers in altitude, still higher than a commercial airliner. And like I said, the slant or the surface distance was only about 18 kilometers, if I remember right. But the flat Earth delta in distance there, the target height error, was about, let me look it up exactly off my Excel sheet here. It was 31.57 meters, whereas for the globe, it was only 3.3 meters. So about a factor of 10 difference, which is not attributable to refraction, because the amount of refraction we expect based on the weather balloon data there, we're talking about 0.01 degrees, okay, of target refraction. The celestial theodolite, or really flat Earth prediction, the flat Earth rise over run angle, is wrong by 0.096 degrees, almost 0.1, almost a tenth of a degree, almost 10 times higher than the amount of refraction.
Well, that's on this chart. See, this is kind of like a different thing, right? So I think there's two reasons why I don't like the way that you compare these things on this particular data chart that you have. One of them is that the reason in the first place that this cell Theo method was ever invented was that it was long known that if you just use a regular theodolite or a telescope with an angle reading function to point at objects and look at their apparent angle at which they are coming in, right, then you can see that the apparent angle of looking at objects doesn't match rise over run, right? Like that's known, and it matches pretty closely in most instances to what you would expect like a geometric globe plus refraction to be, right? Or pretty close to it. So the point of this Theo method was to say, hey, we know that there are optical effects going on that cause, a deviation from what a straight line geometry would expect. Some of those have to do with the way that light traces arcs in space. Some of it has to do with the way that our actual field of vision, as you relate 90 degrees above our head to 0 degrees at the horizon, the angle to distance ratio changes across that angle range. It is not entirely linear throughout the whole range of angles. As it gets closer to the horizon, for example, it compresses and becomes nonlinear. And so there's different sources of this deviation from linearity. So this was intended to be a method to use a physical object between us and the star, assuming that the star is, not measurable, its true position, like physically in space, 3D space is not measurable, right? Because we just see it, it's an apparent light. So let's use an object to block the light to try to see where it really is. That was, the purpose. That's the first point. And I think the second point is that comparing this data to Allen's, right? Allen's data is using just the raw angle with arctan rise over run, whereas you are taking arctan rise over run minus drop over distance plus refraction plus celestial refraction. And
for the globe,
yeah. And so there's a couple reasons why I don't think that's appropriate. Number one is that if you're going to add in corrections, right? Like he's using the raw angle on purpose, and he's comparing in his data set. He's comparing what the raw angle minus drop over distance would be for you, and in all those raw angles, Effie's closer on all those. But then once you add those two corrections in, of course you get closer. That's to be expected. One of those is regular refraction, which you could add back in his. So I guess you could do, arctan rise over run minus drop over distance plus regular refraction, and he could do arctan rise over run plus regular refraction. He would still be closer. It's that last correction that you do, the celestial refraction, quote unquote, that really seals the deal. The magnitude of that is like 6 to 20 times greater than regular refraction throughout these data sets. Most of the time, it's greater than the half gamma angle.
But here's the thing: like this is why I'm picking targets, including the airplanes, where the delta from refraction, the amount of refraction, even celestial refraction, even what I would call astronomical refraction to the star, is less than the difference from what we're seeing comparing globe to flat Earth. Like the 90-kilometer plane here, the star refraction there was 0.147 degrees. The celestial theodolite error was 0.296 degrees. Okay, wait.
This is a plane chart?
This is the planes, yeah.
Why are you comparing celestial refraction to a plane?
Well, again, the plane is blocking a star, right? This is doing it Allen's way of taking the star that's behind that airplane, okay, and figuring out where it should have been, right? This is doing it Allen's way, literally. So we know where the plane was based on the sky, based on the star that it was occluding, right? It's no different than a mountain peak. It's just a plane instead of a mountain peak.
Yeah, and he lives in Florida. There's no mountains there.
Right.
Okay. I feel like it would. Well, maybe we'll look into that plane data later. My initial thoughts are I didn't realize that. I was thinking you were saying that you were taking angles to the known plane position. I didn't think you were saying you were using the plane in place of a mountain.
So the angle to the known plane. Okay, imagine this. The mountain, right? You know where the mountain is, right? You know the GPS coordinates of the mountain peak. You know the altitude of the mountain peak, right?
Right.
So I have to know the GPS coordinates of the plane. I have to know the altitude of the plane. Well, I get that from the ADS-B. That's why I went into the whole explanation of ADS-B. The weather balloon has to convert the barometric, because I got to get to the same starting point, right? Where I know where the plane is, where I know where the plane is, and I know how high it is. But fundamentally, from that point on, this is literally celestial theodolite. This is a plane blocking that star right there, knowing where that star is for the globe, again, with the globe based on refraction, based on the globe drop, etc., and comparing that to Allen's celestial theodolite, where I moved the observer position to the target, the plane's GPS coordinates, and grabbed the angle, the geometric angle of the star, right, without refraction. Okay.
What kind of angles are we dealing with to these airplanes? 10 degrees, 20 degrees, 15 degrees?
That's a fair question. So the angle to the airplane, let's see here, target apparent angle. So this is with refraction. The target apparent angle for the planes range from 16 degrees down to about 5.6 degrees.
Okay, I figured probably like 15 or so. So yeah, I mean, this is somewhat apples to oranges in terms of what we're doing, because once again, until you get below 10 degrees and really below 5 degrees, as definitely closer to 2 to 1 degrees, it increases what I'm about to say. the deviation from linearity in the optical regime of angle to distance ratio changes dramatically. And that is why, for example, in some of the data sets like Blend Mountain and Green Mountain, these observations that are really far away and really close to the horizon experience the most extreme deviations from baselines. That's where you were getting like the 600 meters, 1200 meters, like all this different, various crazy offsets in the predicted height of the mountain based on these things. And you had like 3 or 4 times the gamma angle for the celestial refraction correction. My point is, real quick, I just want to get it out. Celestial refraction, we actually did a dig on this in order to, I got educated. Like when celestial theodolite came out, I didn't know half this stuff. I had to become very educated. The history of Snell's law, right, is very well established. It's a very well established physical phenomenon. It's the basis for refraction. We can plug in temperature and pressure and all these things and calculate very precisely. However, the celestial refraction is a different story. It actually was created because there were deviations between the ideal predictions with regular refraction included and the actual measurements that they were taking to stars. So what they did is they said, we can't quite form a general solution for all of these blanketly with a physical phenomenon. There's no general form solution. So what we'll do is we'll plot a ton of data, and then what we'll do is we'll compare the measurement curve to the prediction curve. We'll take the difference between that, pop it out as a second order polynomial fraction, and then that will be our correction formula. So every time we take a prediction, we run our prediction through this correction formula, and that will predict our actual measured apparent angle. So it's actually just an empirical curve fit at the end of the day. It's not a general solution predicting anything physically.
But do you understand my entire analysis isn't based on a polynomial. It's based on empirical data of what the atmospheric pressure was at each altitude. And it literally uses a derivative of Snell's law to determine what the refraction is. It literally is physically based. It is that's what ray tracing is. It's a physically based simulation.
And I know what ray tracing is.
Yes. But in this case, I'm not ray tracing it like NVIDIA where it's just, simulations for a video game. No, this is ray tracing data based on the actual pressure, temperature, and humidity at each altitude to determine how much refraction there should have been based on the atmosphere. You're saying that it's not apples to apples because I'm looking at things that are higher than what you guys have been looking at. Well, that was deliberate because at higher elevations, you have less variation due to refraction, and we see a bigger difference between what celestial theodolite predicts versus what the globe predicts. That's why the orange line here is diverging from the blue line. It's because of that relationship.
But sorry, go ahead.
And this is the thing, I'm not using a polynomial. I understand, it sounds to me like you're well, okay, I'm not going to make assumptions about where you are in your journey with this, but it sounds to me like you've been listening to Alan for a long time now about this stuff. The thing he wasn't expecting, and the thing that I was bringing to the table here, is that this isn't based on a polynomial. This is based on actual ray tracing of what the ray should have done through the atmosphere.
But no,
and that works with his data too.
I trust that your ray tracing model is accurately predicting Earth refraction, terrestrial refraction.
Celestial refraction too. That's what it's doing. It's doing the astronomical refraction as well as the refraction to the planet.
We'll see. That's the point though. So real quick, getting back to the celestial refraction, that's what I wanted to focus on. The number that you got, right? The number that you got for celestial refraction was within like a fraction of an arc minute of what Alan had in his spreadsheet, and just using these formulas from like the early 1900s for celestial refraction. And they did not, right? All they were doing was empirical curve fitting. The way that celestial refraction is apparently, quote unquote, calculated, they claim that it's analytically calculated now using physical variables. That's actually just through using a relation of physical variables to those empirical plots that were already taken a long time ago. It's still not a general form solution. Like when I take regular refraction, terrestrial refraction, right? It's literally just a function of temperature and pressure. When you use celestial refraction, you have to use a function of apparent angle. Right? You feed it in an angle and it takes a second order polynomial and multiplies it out. Now, there are some combined formulas that combine together terrestrial and celestial refraction into one formula, and they say that they're accounting for celestial refraction through those variables, but they're not actually related. So that was my point, is until you, like if I was to do the same thing, I'll just invert it, right? I'll invert it and flip it on this head and say, I'll take your position, right? If I was trying to prove FE, and I made this rise over run curve that Alan has, right? And then I added regular refraction to it, and I was still way off. I could then say, hey, look, I'm going to plot my predictions for arctan rise over the run plus terrestrial refraction. Then I'm going to plot all my measurements. These two curves don't match each other. So now I'm going to take the difference between these two curves, plot that out as a second order polynomial, and that's my flat celestial refraction correction. Now I'm just going to, every time I take an arctan rise over run, I got to add terrestrial refraction and I got to add flat celestial refraction. And now I get accurate predictions. Look at that. It's magic. It's like within 1 arc minute every single time. That you would never accept that as a real scientific process.
But what you're describing is not what I did at all.
That's where celestial refraction came from. When you're using this formula for celestial refraction, it was derived from that process.
Again, I don't know how many times I have to say this. Look, the fact that I recapitulated celestial refraction based on empirical data from a weather balloon should be telling you something different than what I think it's telling you. I don't think you're understanding the signal here, and you're in the noise. You're not understanding that I literally recapitulated celestial refraction by your own admission based on empirical data from a weather balloon. I didn't start assuming that I needed to hit a certain value and just fudge the numbers and make that happen. No, this came from the weather balloon data ascending through the atmosphere, measuring how that pressure drops off with altitude, and then plugging that in to a derivative of Snell's law to then determine how much the ray should bend.
Yeah, that derivative of Snell's law is what I'm talking about. So if you share that formula with us, I would guarantee, because I've already seen it. I don't know the particulars. Different formulas. There's a whole different set of them for different angle ranges depending on the author, right? That's why.
No, that's not what I'm doing at all. You're not
share
understanding.
It with us. Share us the formula.
It's the source code is in the link in the video description. Okay.
Okay.
It's also in the side chat.
It's also
in the private chat. Let's do a little parenthesis here because we have a couple. Yes.
Yeah, we can hear you.
What's up, you guys?
So
Thanks for having me. By the way, Reds, yeah, great moderation. I think it was not, it was not bad at all. Even though you have a bias, it's fine. What I thought about Alan's opening, I mean, he basically just explained the Theo method, but I just have a couple of questions if that's cool. But unless you're doing like a format thing,
yeah,
I don't know. Okay,
yeah, we can go into open discussion if you can save them for in a little.
Yeah.
We can move on to those later.
Is through Heffron's observations for Pikes Peak, the globe is better. It works better than the celestial theodolite because I'm directly computing for refraction and accounting for everything myself. I'm not relying on stellarium, and I'm not relying on some polynomial. Yeah.
No, that's awesome. I'm just like, is there a difference between, for example, Pikes Peak, right? The first observation in terms of what was the predicted globe angle with and without refraction, right?
That's all there. Yeah.
That's all.
So that's all there. And so the results, the CSV files for everything is on the GitHub page. It's in the video description. It should be. Red's got the link. He's going to put it in the video description.
Oh, it's on Red's channel? Okay.
Yeah, it's at the debate stream on Red's channel. If you go to the video description, he'll have it in there. It's got the GitHub. It's got all the weather balloon data. It's got the observational data, celestial theodolite data.csv, and then there's celestial theodolite results.csv, which
Let me just be clear. It's not there yet, but it will be.
It will be. Okay. So it will be.
You might post that in the chat real quick while we're discussing it. It's a GitHub page, right?
It's a GitHub page. Yeah, let me get it.
Thank you. I appreciate it. I just never seen the data actually with my,
Because so, what I want to do is I want to make sure I have everyone's links so I can post all of it at the exact same time.
That's right.
All of
and seeing if there's a difference in the amount.
And all of this was very clearly stated during the debate, so I kind of baffled why you're asking questions that were like very clear. I even understood that all of this.
No, I just wanted to see a compare and contrast of like what he got for Pikes Peak versus what it shows on Alan's spreadsheet, and seeing if there's a difference in the amount of refraction that was needed in order to, explain the occultation at that time. That's all.
So, like I said, all the results are there. Keep in mind, it's not only the refraction value that may vary somewhat; it's also the star's position. Because what I did, so the RA and the deck of the star that came out of Alan's spreadsheet, I used that as a lookup value to look up the closest star within the Hipparcos catalog. And if I didn't find one within 1/10 of a degree, I discarded the observation as there's no match here. There were, I think, 2 stars that weren't in Hipparcos that were in Alan's data sheet, but the rest of them are all in Hipparcos. So once I find the actual ID of the star in Hipparcos, I then compute for everything. Aberration,
the ideal star, you said? Like, you mean the actual, the true geometric position of the star? Is that
the
ideal star?
It's more basic than that. It's the Hipparcos catalog coordinates. So let me back up for a second. Stellarium is doing a lot of work in the background for you. It's calculating for precession and it's supposed to be doing aberration, all that stuff. Yeah. I'm not trusting it. I have no reason to. I just do it myself anyway, right? So the program that you'll see on that GitHub page is designed to calculate for proper motion, precession, aberration, nutation, all of that, the stuff that Stellarium would do. But I'm doing it from the original Hipparcos catalog data. So I know what my source is. I know exactly what catalog I'm referring to. I don't know what Stellarium's using for any particular star. I could dig, but why would I? I just use the catalog. The catalog information is the J2000 coordinates, the coordinates referred to precession as it was in the year 2000. Okay, so you have to first calculate for the precession of Earth's axis between 2000 and 2026. It's quite significant. Then you have to calculate for proper motion, all that stuff, right? So I'm doing all those computations myself. So okay. The resulting calculations at the equinox of date may differ somewhat from Alan's. So there's that. Then you're calculating the elevation of the star over the globe of the Earth, the spheroid of the Earth, and then calculating for refraction on top of that using my method. All of that is going to differ somewhat from Alan's.
All right, let me hand it over to the plural for thoughts on Astronomy Live's opening, and we need to keep it rotating because we have a bunch of people today here. Thank you, everyone.
Okay, thanks. I thought Astronomy Live's intro was concise. It explained Theo in the way Alan should have. But again, I think it highlighted the fact that Astronomy Live was there to explain the observations and the data, while Alan was there to throw shade, muddy the waters, and basically cast as much doubt on any data and every data as he could, and say, "Ta-da, we win!"
All right.
And again, I think it showed that Alan doesn't understand the maths, whereas Astronomy Live does. Alan doesn't understand the methodology, whereas Astronomy Live does. Alan doesn't want people to understand it, whereas Astronomy Live does. And I think the two openings completely highlighted the differences between the two debaters' positions.
All right. Thank you so much. Steel City.
Well, yeah. I really liked it. It was a very pleasant, easy to follow opening. And I can only speak for me, but it seemed like everyone else in the watch party that we had going was also very impressed that he used a moving plane. So yeah, that was awesome.
Yeah.
Boss.
I had some fun tracking those bad boys. Yeah.
Reds.
Yep. And then after this, I'm going to call it a night. Yes, I know how much work Astronomy Live puts into his presentations, and the reason why I know this is because he won't stop calling me to bitch about it every single fucking day. It's like, oh, I'm working on this, I'm working on that, and I'm going to put it this way and that way. And I go, yes, I understand. Your dick is massive. I get it. It generates its own gravitational field, but that's all to say that he does put a lot of work into his presentations, and puts a lot of work to collect the data, to do the math, to do the analysis, to explain it clearly for us people that haven't gone through the trouble of doing all this work. Astronomy Live has really perfected the art of taking really complicated subjects and making them easy to understand, and that's a skill that he developed over a lot of years, and he started developing the skill after he was introduced to me.
Well, and I have to give credit to Reds here because he was a huge help here. He was there. He was the one who took my picture there with the big telescope where I'm tracking a balloon. He was there that morning helping me out and bought me breakfast afterwards. So thank you, Reds. I appreciate that. Appreciate all the support and help, watching my equipment as I had to go pee, etc., like all that kind of stuff,
I totally get that. No one was going to fuck with your shit while I was there. But yes, Astronomy Live, I think you did a fantastic job, and I cannot wait to honestly host another debate in the future. It's going to be great, because now that the information is out there, now that we're going to give Alan pretty much all the time he could ever need to actually analyze this shit, we should be able to do this again and come back with what can only be described as an even greater debate.